So, I mean, what I've tried to do in this class is to instill in you a particular set of skills. But what I can't necessarily do is give you more energy computationally on a test or something. I mean, I would think working tedious and lengthy homeworks builds up your strength on these sorts of things. But, you know, there's really no time for endurance training before the final, right? That time has come and gone. So at the moment, you got to think about how to fight smarter, not to fight harder. So as we look at these problems, one of the things I want you to notice is sometimes I've asked a certain question. For example, problem 5, I said, find the formula for Q of V in terms of eigenfunctions. How many people here worked problem 5 and found eigenvectors? Didn't need to. Didn't need to. You can find the formula without finding a single eigenvector. Lame. But true. Or in problem 4, how many of you found a Jordan basis here? Didn't need to. Didn't need to. Because you can find the real Jordan form just from looking at less data. If you find a couple of, you know, once you learn certain things, you know what the real Jordan form is, right? You can extrapolate from a certain limited data set what the Jordan form has to be without actually finding a Jordan basis. Now, of course, finding a Jordan basis has a certain, you know, there are things you can do with that explicitly that you couldn't unless you did. I mean, there are advantages to finding that, but if the question doesn't involve those things, you're wasting your time, right? Just saying. So problem 1, this is just basically, hey, we learned determinants and their properties, so do that. So the determinant of a block is the product of the determinants of the blocks. You notice that this pulls out -1 cubed because A is 3 by 3. This pulls out 3 to the 4th because B is 4 by 4. All right? Common mistake here, just pull out 3 or minus. Don't worry, we'll still give you at least a quarter credit. Just kidding.
Oh, for what?
I
know.
Will you post this?
Yeah, of course. Any questions about this one? All right, let me move on. Problem 2.
Michael has actually.
Oh, yes, my
Should we turn in our quizzes before we go over this?
Oh,
Because
that's
I'm very
probably-
tempted to fix a stupid mistake I made.
I mean, I wouldn't actually mind you looking at the quiz as we're looking at this, as long as you promise not to modify it.
I promise.
Promise?
I solemnly swear I'm up to no good.
All right.
Kidding, I don't.
I'm going to hold on to them then. I think you guys know what you did. But, okay, problem number 2. You were asked a bunch of stuff, right? Let's remind myself what it was. Define W as the span of this and that. Find an orthonormal basis gamma 1 for W. Find an orthonormal basis gamma 2 for W perp. Set beta equal to the union of those two. Calculate the coordinate vector for 2, 2, 2, 2. And also calculate the projection onto W and W perp for that being. So, I mean, a lazy person would have wisely chosen not to do this one. But you had 6 to do.
But I didn't.
You did it?
What challenge accepted? I started to do it, then stopped.
This is by far the most difficult problem on this quiz. Maybe the last one on this. So, to find an orthonormal basis,
I know.
to find an orthonormal basis for W, you already have a linearly independent spanning set, so you just run that thing through the Gram-Schmidt algorithm, right? Normalize the first thing. There you go. 1/√3. And then I do the standard thing. I subtract off a piece in U1 direction. That gives me this vector. You guys got to be more careful with fractions. Bailey tells me that you're all very, very bad at it. Sorry.
Thanks, baby.
Numbers are good, yeah.
She also said you're bad people.
Hey.
I like her. She gives me credit for just writing down questions.
She's gonna read your next one so hard.
So
There is no next one.
The quiz.
name calling and criticism of your arithmetic aside, when you're done with the step and the Gram-Schmidt algorithm, when you get to U2 and you normalize it, even before you normalize it, right? By the way, I ignore this third and I just take this squared plus this squared plus this squared plus this squared, divide by it, and just throw away the third. That's how I come up with this. That's the fast way to normalize a vector. Ignore the scalar multiple in front and just normalize the integer part. So if you're right, the dot product of U2 should be 0 with U1. If that's not true, you need to stop and fix it, right? Yes?
Can you repeat what you said?
You need, what? I said when you get to U2, you have to take the dot product of this with U1. And if it's not 0, then you did something wrong. Because it's supposed to create an orthonormal set, right? So this is your orthogonal. The normalization is kind of less critical, right? You could normalize it wrong. You wouldn't be able to pick up on that until you calculated the length. But yes, Landon.
So, assuming this is like on a test, if we did do the dot product and found out it was not 0,
Then you
but
have to do this thing, which is check your work, find the mistake.
could you continue with it wrong and show at least we know what to do after that, even though it's wrong, and get more partial credit instead of wasting more time on the problem, or what would be the better option?
I don't know.
Not mess up.
I know, but I'm certainly not going to answer that question and give you license to be careless with arithmetic. Because many of you are far too careless with arithmetic, and you need to fix that. Because it will kill your scores on standardized tests later. Yeah.
What did you do with the 1/3 times to get that Eigen? You just drop it off? What happened to it?
Oh, if I have a vector, say CV, and I want to normalize it, or say CW. Suppose I want to normalize that, right? So then, if you put a hat on it, what that means is that unit vector in the same direction. So what you do is you take CW divided by the length of CW, basically, right? But if you look at that, that's C over the length of the absolute value of C, W over the length of W by the properties of the norm. So this is just plus or minus 1. So you can ignore it. And just instead focus on, just take the W and just normalize the P. So here, W is the thing without the thirds. It's this. So I can just normalize that. That's the square root of 78 comes from that. I don't do the square root of 25 thirds plus 36 25 ninths plus 36 ninths plus a 9 plus 4 ninths. That's not a good use of your time writing, and it leaves you with an uglier answer, which is hard to see what you're doing. So if you can get rid of fractions, get rid of them. Right? Like those friends from high school you don't call anymore. Yeah.
As you just hold. Max didn't know with it.
Yeah, I was homeschooled. It's
Your mom.
I was homeschooled, but I had my phone.
Did you say your mom? What? Who tricked you?
I was thinking your mom.
I heard that. No, so the point is just this. Ignore the fractions and focus to see if you did it right or wrong. All you gotta do is take the dot product of this with minus 5, 6, 1, 4, right? If this is equal to 0, then at least you've got the orthogonality right. So that's what? That's minus 5 plus 0 plus 1 plus 4, which is minus 5 plus 5, which is 0. Okay. At least it's orthogonal.
I'm proud of you.
Oh, good. I'm glad, because I checked it earlier, so I knew this would work.
It's just a lot easier.
I know, given other days in this class, you might expect that there would be a mistake here, and then you could laugh at me, but that's probably not going to be a theme of today, at least as far as mistakes
We haven't
go.
coughed yet, so.
I haven't coughed yet. Hey, stop that.
So now if you do make a mistake, it's twice as bad.
Okay, so all we've done so far is to find an orthonormal basis for W. I also asked you to find an orthonormal basis gamma 2 for W perp, right? How do you do that? There's a couple, yes.
You find the null space.
Of A transpose.
Yeah, find the null space of the generating set transpose, basically. So find the null space of this guy. So you just do row reductions. Now, this notation here basically is I did a row operation. I'm not telling you which one. You're also free to use this, but if you make a mistake, it kind of burns your partial credit. So I don't care about partial credit, so I'm not worried.
You divided by 2.
What did I do here? I don't know. I mean, yeah, I divided by 2, but sometimes I'll do many row operations in one of these squiggles. I can see what the, yes.
So we're allowed to use that notation?
Sure, but like I
Okay.
said, it burns through your partial credit.
But if we get it right, it won't matter, right?
Right.
Okay, good.
I'm just saying,
It takes me a long time to write out all the row operations.
Right,
and
right,
so
right.
And I can just scribble random
Now,
stuff on a scrap
there
paper.
is a caveat to that, which is of course is in the, there will be some problem somewhere on the exam where I say explicitly denote,
Well, yeah.
you know, the row operation, but everywhere else. At one point, Well, I mean, usually every final exam in linear, the first question or something I ask, will we solve a system of 3 or 4 equations? You know, that's usually a question, and I don't even force you to use one method or another. You know, I have to find the solution, something like that.
Does Wolfram count as a method?
You're not allowed to use Wolfram alpha, we're fine. It's not the case. Yes, David.
Could something else you have done is randomly guess 2 vectors that you thought to be linearly independent, and then show by regression that they are linearly independent and outside of W?
Well, here's the problem with that. If you could randomly pick 2 vectors which are perpendicular to the vectors of W,
Well, not perpendicular, but just linearly independent.
well, then you got to run Graham-Schmidt algorithm on 3 or 4 things, and that's computationally much more expensive.
So that's why it gets asked if you do that.
Right? I mean, that is a method. You can just pick vectors outside W and then subtract off the pieces which are in W by using basically the projection, essentially. But that's a lot more.
And don't do that.
I would say no. I'd say it's easier to calculate the perp directly using the null space calculation.
Okay.
So.
And doing this gives you the actual perpendicular orthogonal textures. and stuff.
Right. This well, the calculating the null space is the transpose of the generating set. This right here. That immediately leads me to writing the perp as a span of 2 vectors, right? Now these vectors don't have to be orthogonal. In fact, they're not. If you take the dot product of this and that, you get what? 2 plus 3 is 5, 5. You get 5. Dot product of that and that is 5. Those are not orthogonal, right? So that will not be a basis gamma 2 that we're looking for the perp. However, it is already the case, you can easily check that this and that are perpendicular to the vectors in W. You can take dot products of those with this and that and you'll get 0. Okay? So it's at least that. So that way, that means that if you were to think about doing the 3-fold and 4-fold Graham-Schmidt algorithm, it kind of trivializes into just being about the last 2 vectors as opposed to the first 2. Yeah.
Is that a negative 0?
I refuse to answer that question. All right.
No, actually, I was wondering, is that 0 or is it supposed to be like something?
It's negative 1. Should be 1.
What I did? Oh, that's a 1. That's a -1.
That is not a 1.
It was a 0, but it became a -1. That's much -1. Here it's more clear. I have multiplied by -1 to make more 1s, and multiplied by 2 to get rid of fractions. As you know, I hate them. And there you go. That's a nicer. So when you can get rid of ugliness, do it by multiplying your generating set by non-zero scalars. That's what I did. Make my life easier. So then U3 is my first in gamma 2. And then I do Graham-Schmidt again to calculate U4 tilde. But then again, there's a third. I pull it out. I just normalize the 1, 4, 5, 6. Again, that's those sums of the squares are 78, just like the other one. And there you go. That's your 4th vector. So if you put these, that gives my basis for W perp. And then when I put these all together, I have a basis for R4, which is orthonormal, and respects the decomposition into R4 into the direct sum of W and W perp, right? Anyway, a lot of words, but I hope you see the calculation. So then I want to calculate the coordinates of this vector 2, 2, 2, 2 in terms of the basis, gamma 1 union gamma 2. All I have to do, right, is calculate dot products of V with U1, V with U2, V with U3, V with U4. Those give me the components, right? And so that calculation is relatively simple. It gives me 6/3 or 6 over 3 times the root 26. I guess this is, well, anyway, whatever it is, it's coming from the 78 and the root 3, or 2/3 for this one, or 4/3. And so this piece that's coming from the dot products with gamma 1, this gives you the projection onto W, and the other piece is the projection onto W perp. Of course, this could also be identified as being the orthogonal projection. That's the piece which is off W, right? This is the piece which is orthogonal to W perp for what it's worth. So there's always this mirroring between the projection and the orthogonal projection for a subspace and its complementary subspace. 2 subspaces are said to be complementary if they're like this. You know, if you have W1, direct sum W2 is equal to Rn. These are complementary subspaces. But when these are also orthogonal, right, then you have this interplay between orthogonal and projection that I was just talking about. Okay? The projection of the W1 will be the orthogonal projection of the W2 and vice versa. questions about this? Yeah.
Yeah, when you do like a projection, don't the square roots usually end up canceling? Because you get like one square root from the from the inner product, and then another one from
Have I forgotten my?
Yeah, because I don't.
I think your v dot u2 and v dot u4 aren't right. Because it's over square root of 78, not square root of 3.
Ah, phooey. Well, there you go. You happy, Sharon? She is happy.
I mean, she got a grade, so.
Hey, where's the ring?
I literally.
It's getting resized.
So anyway, yes. So the spirit is willing to flesh is weak. I mean, this is the right idea, but the numbers in front are wrong. Okay, at least for this one
And the fourth one.
and the fourth one. So this and that need to be fixed. Okay. Did you guys get any of it? At least.
Very mean man.
What's that?
I said it's a very mean man.
Oh.
Oh, I did this right.
Yeah, this is not complicated. So I got an email at least from one of you who was like, "Am I right? It seems easy. Doesn't have to be
I
complicated."
wrote that on my papers. I
Um,
think it's this book. It's usually easy, so I don't know if it's right. But if I did it right.
So the second derivative operator, if you differentiate e to 2x twice, you get 4 times e to 2x. Differentiate e to 3x twice, you get 9 e to 3x. Differentiate sine twice, you get minus sine. So these are all eigenfunctions, or if you like, eigenvectors, with eigenvalues for 9 and minus 1 respectively. And so that means if you calculate the basis of t, the matrix of t with respect to this basis, or beta upper beta if you like, we get 4, 0, 0, 0, 4, 0, 0, 0, 9, 0, and 0, 0, minus 1. That's it. So what would the determinant be? The determinant's the product. So the determinant would be minus 36, and the trace would be, what did it say? 12. Okay. So, you. Problem 4 continued. What? Sorry, apparently those got out of order.
Just one thought.
Find the real Jordan form of block. So, first of all, with any of these problems, unless you're given extra data, you just have to face the music, calculate the characteristic polynomial. So I do that, and I always look for factoring by grouping. Like here, you notice there's a 1 minus lambda in both terms, so I can rip that out, and then just keep what's left over. What's left over is 2 minus lambda times 2 minus lambda, which is 2 minus lambda squared, and a minus 1 times minus 1, which is plus 1. And then you flip it over, and then you know how to read it quadratic. This is a completed square quadratic that's coming from a complex root. So I can read immediately from this that that's 2 plus or minus I, complex eigenvalues, and lambda equals 1 is my first eigenvalue. Once I read that off, I know what the Jordan form is without further calculation. The Jordan form is a 1 in the upper block, and then the rotation dilation block, 2 minus 1, 1, 2. This guy. What do we get from 2 plus or minus 5?
How do you know
Because what we worked out in section 11.7, we know that if you have A times A plus IB is equal to alpha plus I beta times A plus IB, then it follows that A is equal to alpha A minus beta B, and AB is equal to beta A plus alpha B. And so what that means then is if you look at like a two-dimensional case for a second here, if this is my choice of letters, if my basis gamma is AB, then and if I have T is equal to AB, T of D equals A, so that linear transformation, then the matrix of T with respect to the gamma basis, well, it's the coordinate vector of AA, coordinate vector AB, right? But the coordinate vector of AA is just alpha minus beta, and the coordinate vector of AB is beta alpha. Do I have minus for the wrong place? Ah, sorry. But you see that that's an ambiguity. That just means that I've written the block for the minus eigenvalue rather than the plus eigenvalue. So You could still say that that's right, it's just not consistent with what I was doing. I really should have the plus and minus switch there to be consistent with my typical nomenclature. So that's the block that corresponds to the complex eigenvalue. If you use the real and imaginary parts of the complex eigenvector as basis.
Could you also have found, like, found your characteristic polynomial and then found your inverse, found your eigenvectors, concatenated them, found the inverse, and then multiplied the inverse times A times.
You could do that, but that would be a lot more work, right? So how to obtain the Jordan form from A? Yeah, you can find the eigenvector with eigenvalue 1, which in this case would be something like 3 minus 6, 15, right? And I might ask you to do that. So I'm not saying that you don't need to do that. I'm just saying don't do it unless you need to do it. Oops. And then working backwards. And then the complex eigenvalue here, I end up with, after some row reductions, 1, 0, I, 0, 1, 0, which gives me y equal to 0, x is equal to minus iz. So basically I have this fundamental complex eigenvector minus I, 0, 1. I break that into the real piece and the imaginary piece, and then that gives me the basis. The eigenvector with eigenvalue 1, the real, the imaginary part. That similarity transformed on A will bring me to the Jordan block I started with. Not quite, because I had a sign error. You know, like I said, that will actually bring me to, the way I have it set up currently, actually there'll be a minus here and a plus there. So there's a sign error currently. Because I have, if I put A and then B, then it puts a minus here. See? Okay, Lou? C. I'm just doing C. Am I seeing myself or C?
No.
Here, this part. This is where the minus is. All right. Okay. Does that answer your question? Or does it just raise new ones? Okay, but technically I just asked for the Jordan form of A. I didn't say show me the similarity transformation to produce it, did I? I did not say that.
Will you on the test?
Maybe. What I'm trying to tell you is if you understand the theory, you can use it to circumvent calculation. Right? That's part of the point here. All right, moving on. Number 5, we have a quadratic form. So the first thing you need to be able to do is write the matrix for the quadratic form, right? Sometimes I'll just ask that as a question, write the matrix for the quadratic form, right? That's a pretty easy skill to pick up, right? You put a 1 wherever you got x squared. If you got a y squared, you put a 1. If there's no y squared, there's a 0 in the middle spot, right? If there's no z squared, then there would be no, there would be none of this right here. Now, just to remind you what our starting point was. Sorry, I was being lazy, not writing out the problem to start with, bad form, but hope you can forgive me. So the reason there's 1s down the diagonals is x squared, y squared, z squared. And then you got 4, minus 4, and 4. That's putting the 2's in the 1, 2, and the 2, 1. This puts a minus 2 in the 1, 3, and the 3, 1 spot. And this puts a 2 in the 2, 3, and the 3, 2 spot. The reason that we write the matrix symmetrically is because we can, and because we know if we do, the spectral theorem applies, which means we'll get real eigenvalues and a super awesome orthonormal basis. Although I haven't defined the technical meaning of super awesome. So. I feel like it's manifest, whatever that means, it's it. So what is not entirely super awesome is calculating the characteristic polynomial of this. That's just work. It's always just work. You can make less work if you use row reduction, right? So like if I add row 2 to row 3, puts a 0 here, right? And then what did I do? I added row 1 to row 2 to row 1, and that puts a 0 here. I know having these zeros, it's it's nice to have zeros. Like if you can create zeros in the matrix through simple row additions, it probably makes the characteristic polynomial easier to calculate. That's just my intuition. Now some of you may have just wrote the determinant out from here and just took your medicine. I mean, that's fine, you can do that. I don't really care how you calculate the characteristic polynomial, as long as you calculate it correctly. So when you do, after a bit here, I expand on the top row, I think. Yeah, so 3 minus lambda times the determinant of this subblock, which gives me this times this, minus that times that. And then minus 3 minus lambda times this subdeterminant, which gives me just 2 times 3 minus lambda. Take a step back and look at it. You notice that you've got 3 minus lambda squared on everything. There's 3 minus lambda, 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 3 minus lambda. Every summand here has a 3 minus lambda squared, so factor it out. This is basically factoring by grouping. And so that gives me 3 minus lambda squared, and then over here I've got minus 3 minus lambda. So I end up with an eigenvalue 3 with multiplicity 2, and eigenvalue minus 3 with multiplicity 1. Algebraic multiplicity, of course. Although we know that algebraic multiplicity is equal to geometric multiplicity for a symmetric matrix by the spectral theorem, we know that there exists an orthonormal eigenbase. So we don't need generalized eigenvectors for a symmetric matrix, right? Just saying. And so once I know that, I can write the formula. Because the formula in eigencoordinates is always lambda 1 y1 squared plus lambda 2 y2 squared plus lambda 3 y3 squared. Lambda 1, lambda 2, and lambda 3 here being 3, 3, and minus 3 respectively gives me that. That's the formula.
Why did you choose 1 squared?
We work this out in general. Here, let me work it out again. So, suppose I have Q of V equals to V transpose A V, right? And then I want to do a coordinate change. I basically want to let my V bar equal to beta inverse times V, right? This is my coordinate change. And here I'm going to let beta be, let's say V1, V2, V3, eigenvectors, right? With eigenvalues for us 3, 3, and minus 3 perspective, okay? But I could do this in general. The point is, if I look at this, I've got Q of V is V transpose A V, and I just really want to convert that to V bar, right? So to do that, what do? Oh, by the way, spectral theorem says what?
There exists an orthonormal basis.
Right, so on beta inverse is actually beta transpose. Because I know that beta transpose beta is equal to I. That's orthonormality in matrix form for the basis, right? So, just gotta be creative here. Let's see here. So this is V transpose. What do I got? I got myself a beta. Beta transpose A, beta transpose B. See, all I did was I put in copies of the identity matrix. This is allowed. Yes, sir. It should be allowed. Now, what I have in the middle is a similarity transformation, right? And if you want, I can work it out, but what that is, of course, is what?
Thank you.
So on the one side, I've got my V bar transpose. I've got the diagonal matrix, and then I've got V transpose again. I mean, in particular, this is Y1, Y2, Y3, lambda 1, lambda 2, lambda 3, Y1, Y2, Y3. So I get lambda 1, y1 squared plus lambda 2 y2 squared plus lambda 3 y3 squared. When you work it out, multiply this out. Now, if you don't believe me that this matrix is the diagonal with the eigenvalues, I can go into detail there too. Like, what is beta transpose A beta? It's nothing more than beta transpose times, well, AB1, AB2, AB3. What are those? That's lambda 1 B1, lambda 2 B2, lambda 3 B3, right? And then when you work out the details of that, you get lambda 1, lambda 2, lambda 3. I'm gonna go on though because we have other stuff to talk about today, and I could easily eat up 20 minutes deriving this in more detail, but that would be kind of beside the point. The point is, if you use eigencoordinates, the formula for the quadratic form is simply eigenvalue, eigencoordinate squared plus next eigenvalue, next eigencoordinate squared plus so forth and so on. So the spectrum, which by the way is the list of eigenvalues in increasing order, completely determines the nature of the quadratic form. Yeah.
And this is good because they get rid of them like x times y and
Right. Yeah. That's in fact the case. The formula sums of squares with no cross terms is much easier to analyze, right? If you want to set all of this equal to a constant, if there's any negative terms, it's some kind of like hyperboloid of some sort or another, perhaps a higher dimensional version. If they're all pluses, it's basically some sort of ellipsoid. If you had this equal to a constant. If this is describing the quadratic piece of a function near a point, if they're all positive, then that point is something like a local minimum. If they're all negative, that point is something like a local maximum. If some of them are positive and some of them are minimum, the eigenvalues, if this is the Hessian for the second derivative term in a multivariate Taylor expansion for a function, that would imply some sort of saddle point. But anyway, I'll cover that in advance. We stop talking about that here, because we don't know what a Hessian is. Well, I guess if you read the book, you have some idea. What I'm trying to tell you is if you really understand this quadratic form, eigencoordinate stuff, it's a key to understanding any other place in math where you encounter a quadratic form written in an ugly way. You can always kind of choose eigencoordinates to make the analysis much simpler. In eigencoordinates, the analysis is simpler. That's all I'm saying. Hey, here's a nice question, right? You're like, this problem seems like a problem from a different course. Fine. This is a pretty standard problem. Find the eigenvalues and basis for each eigenspace for 1, 4, 2, 8. The thing that jumps out at me immediately about this problem is row 2 is twice row 1. So I know that this matrix is not invertible, which means it has determinant 0, which means one of the eigenvalues is 0. Right? Because the determinant's the product of the eigenvalues. How can you have a product of things be 0 unless one of them is 0?
it's kind of hard.
You're like, yeah, you're just not in the field. You're something with 0 divisors. Stop it, you know, you're evil. Your brethren do not know these things. Oh, you don't either? Come on. Hey. It hurts. Yeah, really. Okay, so lambda times lambda minus 9 is what I get when I calculate the characteristic polynomial. Just a bit of advice again. If you calculate the characteristic polynomial and you had found, say, 2 and 7 for fun, if you calculated, you know, a minus 2i and a minus 7i for the given matrix, what would you find for the null space of these? In fact, what would you find the null space for anything except for 0 and 9 to be for this? 0. Just 0. Why is that? Because the determinant would be non-zero for these matrices, right? Those are invertible matrices. The only thing that's in the kernel is 0 itself. The homogeneous equation has only the 0 solution. So these are the only. So what I'm trying to tell you is, if you do calculate the characteristic polynomial wrong, what you're going to find when you look for eigenvectors is just 0. That is your hint to go back to the start and fix it. Go back to the start and fix it.
If we keep going, you might give me partial credit.
Do not tell them that. It might be true, but do not tell them that.
Okay.
When we find mistakes, we should fix them.
We have a state every test.
We should not calculate things we're not asked so that we have sufficient time to calculate the questions we are asked.
We should write shorter tests.
We should write shorter tests. Okay,
No, I'm just
I
kidding.
can do that.
Don't make like.
I like your
no
physics
problem.
profile. That was
I
really
can do
nice.
that.
Yep, it's short.
Sharon, I will write
I
a
think
shorter
so.
test.
I don't think
Two
I like
problems,
what you're saying.
each
but-
worth
Each
one has like 40 class.
There'd be 3 problems, one for each test. Right?
I mean,
If it's
depends
the
on what
exact
you
problem.
choose.
I'll tell you which problem it is? Yeah, that's how. Okay,
In
so
our notebook.
A minus 9i
Probably
is
need
this.
to figure out what I'm trying to
So
write.
the reduction, so any questions about the eigenspaces here? Can I
Wait, are we
go?
allowed to have a note card?
I wrote it.
What?
Are we allowed to have a note card?
I don't think I said that.
Okay, Sharon did.
Obviously, we get one.
Sharon is thinking about the third test of number theory,
We get 2.
which I have given you 2 note cards for. I mean, I've allowed you to bring 2 note cards for. Well, I mean, if you want, I could bring the number theory questions here, and then you could have 2 note cards too.
I disagree.
You want me to bring in number theory questions for the final, then you can have. Daniel says yes. It's evil. Yes.
Number theory sounds interesting, so there is that. But I kind of don't want it on my final because I haven't really studied for it. But I mean, I could get some.
You're saying, like, the whole thing you're saying with 0 thing, it's like, you aren't gonna get a, you're going, the only way you're gonna get a non-trivial is if you have something that's in the null space, and I can
Assume that 4 is a number theory.
Right. The dimension of A minus lambda I is going to be 1 or greater only when lambda is actually equals to get its eigenvalue. If lambda is not really an eigenvalue, then A minus lambda I is in fact an invertible matrix, and the kernel is trivial. The null space is trivial.
So for all invertible matrices, the only eigenvalue is 0.
Clearly, it's true.
Or the
There's no, I've never tried to say something about, I mean, I can say this. A not invertible matrix has eigenvalue 0. But what can I say about the eigenvalues of an invertible matrix if they relate to invertibility? Only that they're not 0. That's about all the data I got there. It's not, I mean, there's lots of questions about eigenvalues and eigenvectors that I could ask that seem relatively simple that would be really difficult. For example, suppose you have 2 linear transformations, and each one of those is diagonalizable separately. When is it possible to diagonalize both of those at the same time with respect to the same similarity transformation? That seems like a reasonably simple question. Can you answer it?
When they have the same eigenvalues?
No, they could have different eigenvalues. Maybe T has eigenvalue, one set of eigenvalues. I mean, for example, here's a case you can. If I have T and T squared, right? If T is diagonalizable, T squared is also diagonalizable. So here's a pair of operators which can be simultaneously diagonalized. How do you understand that in general? You don't know? Yeah.
Could you explain it?
I have not explained that, in fact, no.
Could you?
You can, a later point in time.
Could you not explain it?
You're so funny, Chris.
To the love.
Is he as funny as your
She's feeling
fiance?
love. Keep it coming, Sharon. I can go on.
All right.
Or maybe he is your fiance.
I can go over them. I can go over time if need be. No? Okay. So, to calculate the orthonormal basis for W perp, first you must find W perp. I think the easiest way to do that is to do the null space of the transpose calculation, right? So you do your row reductions, bam, you get this thing. And then once I have that, of course, I can write what's a typical thing in W perp look like. It's some kind of span of these 2 guys, right? A span of those 2 vectors. And if those were orthonormal, orthonormal already, that'd be super nice, but that's usually not going to be the case. So then what do you gotta do? Gram-Schmidt, right? So you Gram-Schmidt those, and out pops this orthonormal basis for the perp. 0, minus 1, 1, 0, 0, 2, minus 1, minus 1, minus 1, 1. And if you take the dot product of these two vectors with the original triple with which we calculated the perp, you'll find that each one of those is 0. So those are in fact in the perp, and they are of course orthonormal because that's what we did. I mean, we ran the Graham-Schmidt algorithm on them, we did it correctly, so we in fact got an orthonormal basis. So I hope I have done enough on this quiz that you can see the importance of Graham-Schmidt and also how to calculate the perp given a vector space in Rn, right? Those seem like kind of important calculations for you to be able to do. And also, you need to be able to calculate determinants, right? You need to be able to calculate the characteristic polynomial prime. I mean, I don't usually ask you a naked determinant question too much. I mean, there's some, just a determinant alone. You said you're still 12? What? Seems all right. No. Well, I don't know. I'm trying to gauge the age level.
You should do us candy.
Middle school age level.
I missed the start of all this. It's okay though. I can just.
All you need to know is Sharon's now
Just
engaged.
Just know that Sharon's engaged.
No, not. You said not, right?
Any questions about this problem? Let me go on. Because I think that's pretty much the same as the earlier problem, just less complicated. Problem 8. Here, I gave you a super big matrix and a kind of compact notation. What does this notation mean? Do you guys understand that? I'm saying that A is this ginormous matrix. 3, 1, 0, 3, jump, 3, 3, 4, 1. So am I? You guys are not going to be bothered if I use this block diagonal. I mean, you're not going to lose you on the final if I use this compact notation for block diagonal, am I? I hope not, because it saves me a lot of space.
Is that the same thing as the question?
That's my point. Yeah, that's what I mean when I say 8. Is that
So you just mean that that's all one?
yeah, everything else is zeros outside those blocks. So that's what that notation means. It's just A is equal to this. All right, so first of all, the eigenvalues, 3, 3, 3, 3. Read them off the diagonal, 4, 4, 4, 4. So we have eigenvalue 3 with algebraic multiplicity 4, algebraic eigenvalue 4 with algebraic multiplicity 4. Both have multiplicity 4, right? What's the dimension of the first eigenspace? How many eigenvectors? 3. Yeah, 1, 2, 3. So the first column in any block gives you an eigenvector, and any singleton blocks give you an eigenvector each one. So for eigenvalue 4, I've got 1, 2 eigenvectors. So my dimension of the second eigenspace would be 2. In terms of eigenvectors, I've only got 5 of them. You can see we're missing 3 vectors to make a basis for R8. Those remaining 3 vectors are going to come from generalized eigenvector order 2 for eigenvalue 3, which is paired with the eigenvector, in this case E1. And then there's 2 generalized eigenvectors of order 2 for the eigenvalue 4, which are associated to these columns right here, the 6th and 8th column. So the characteristic polynomial has to be is the higher order is the size of the matrix, 8 by 8 matrix, 8th order characteristic polynomial. So 3 minus t to the 4th, 4 minus t to the 4th, that would be the characteristic polynomial. The minimal polynomial has to be monic, meaning it has to have a leading coefficient of 1. And basically, you look for the largest block for each eigenvalue. That's the result that we've almost proved. At least I gave you a plausibility argument for it. So this is the largest 3 by 3 block. This is the largest eigenvalue 4 block. Well, so is this. But anyway, so you have, I needed a t minus 3 squared because of this. And I needed a t minus 4 squared because of this.
Because it's 2 by 2?
2 by 2. The largest 2 by 2 block, either one, pick it, So you look for the largest block. That tells you what's the minimal polynomial. Now the minimal polynomial has m, or if you like m of a, or if you like g of a. I mean, he uses g, the minimal polynomial in the book. I'm just saying you might use m for minimal if you wanted, whatever, just language. When you plug a into the polynomial, you'll get 0. And it's fairly easy to see why that would happen. For these, if I take t minus 3 if I take A minus, if I take A minus 3I, you see what's going to happen? You're going to get rid of all these. And so basically you end up with something strictly upper triangular, this upper block. When you square it, it goes to 0, but you're left with stuff down here. But on the other hand, when you look at A minus 4I squared, you remove the 4s, you've got this strictly upper triangular block down here. When you square it, that's going to go to 0, but it's going to leave you stuff up here. But when you multiply those two things, you've got something like a non-zero times 3 zeros, non-zero times 3 zeros. So when you multiply those, block multiplication gives you 0 total. I'm just telling you why the minimal polynomial works. That's not, I don't know why I'm telling you. I shouldn't tell you. All right, so I then asked you to find the tableaus corresponding to the restrictions of the map. All right, so there's two restrictions to look at. There's two generalized eigenspaces here, one for 3 and one for 4. So K1 would be the kernel of T minus, I defined T to be the linear transformation associated with A. So K1 would be the kernel of T minus 3I to the, why the 4th power? Because we have algebraic multiplicity 4. And that's why there's a 4 on both of these, for K1 and K2. And if you look at the restriction of T to K1, you get a nilpotent mapping, and n1 to the 4th is 0. And the cycle below is this, because I had 3 eigenvectors and I had one chain of length 2. And for K2, when I look at the restriction of T minus 4I to K2, I get n2, which again is nilpotent, n2 to the 4th is 0. This is the cycle below that case because I've got 2 cycles of length 4, 2 eigenvectors, 2 generalized eigenvectors. That's questions? All right, and then finally, oh man, I have 2 more. I'll be fast. So this one, basically you piece it together. If you look at it, you've got a generalized eigenvector order 2, corresponding to eigenvalue 3 rather. That's what I get from these two when you put them together. This tells me I've got a complex eigenvalue of 2 plus I, right? That means that there's a 2-dimensional subspace, which I can get a basis from the real and the imaginary part of this vector to cover, right? So the dimension corresponding to that's at least 2. It's got nothing to do with the 3 eigenspace or the 0 eigenspace below. The 0 eigenspace, since I've got a non-trivial element in the kernel of T squared, because B5 is non-zero, that means I have at least I have another eigenvector with eigenvalue 0 as well. And it has to happen in theory. So you put it together, you've got these 3 separate subspaces. Each has dimension greater than or equal to 2, but the total dimension is 6, which means they have to each be 2. So that forces me then to say that what I have is all I have. What I gave is all that I have, basically. And so the minimal polynomial and the characteristic polynomial are in fact the same because there is no double, there's no more than, there's just one block for each thing. There's this 2x2 block for 3. There's this complex, like that thing we talked about with the 2, 1, minus 1, 2 earlier, that term. And then there's the 0, 0, 1 with the upper diagonal corresponding to the T squared, the other thing. And the characteristic minimal are the same. And then finally this one, I have a sketch of the proof, but basically the thing is if you've got A to the n, 0, and you've got B to the k, 0, if you look at the product, if you look at CA plus B to the n k, because A and B commute, you can prove that the binomial theorem applies. So you can look at it as a sum of powers of A and A's and B's, and then you can eventually argue that A to the I, B to the I has terms with each power being larger than the trivializing power, and consequently the whole product is 0. That one probably needs an induction argument to be done right or something. That's basically it. Thanks, guys. So Wednesday, I'm hoping we can just come to this room and I will answer your questions about the previous 2 tests. And,
What time?
whatever you want. Not class time. Yes.
How can we be most productive in studying for this test? Like from homework or for the test?
I would start with tests and then branch out to homework.
What about the quizzes?
Yeah, test quizzes and then homework.
Okay.
Yeah.
And the exams on Friday?
Yeah. Do you know something I don't know?
Yeah, we're expecting to be the 0